just to recap, this is the last chapter of the A&P material. We have today's lecture, we got Wednesday's lecture. On Friday, we're going to be having a review session for the last unit test, the last midterm, which will cover chapters 7 and 8, so the nervous system and senses. That will be held on Monday, April 27th. And then on Wednesday, which is technically the last day of classes, I'll have a review time for the final exam. I'm still figuring out the final exam format, the format for the next unit test. I'm also still finalizing. I will give you more details about that on Wednesday's lecture. So on Wednesday, I will update you with what the last midterm will look like and how you can best prepare for that. But in the meantime, you should be studying material from chapters 7 and 8. I assume the format will be similar to the last midterm or our first Canvas test, but I'm still working out a few kinks. Okay, so I first want to show you Canvas and the last few things that are coming up due here. Okay, so this is your Canvas page. On your assignments, you can see that there is really not a lot here. We got that cranial nerve worksheet. That's our last kind of activity. And then you've got your last 2 discussion questions. So in discussions, you've got the last week of things you found confusing or interesting needs 1 post this week. And then there are some questions about the senses, about this last chapter, that needs a post. And that is it for the material for Canvas. So I will take any questions you guys have. I'll switch over to PowerPoint. I'll let the chat feature open. Oh, this is a different class here. Okay, 8. Awesome. Okay, so where we had left off is we had been talking about vision. We had been going over the structure of the eye, and the different parts of the eye that I want you to know. And now, and we talked about how light travels, the path that light takes, right? Going from approaching your eye all the way through. So I'm going to recap for a second with a picture of an eye. Sorry to go back. Okay, so this is what your eye looks like in the sagittal section. Okay, so as light is approaching here from the left, it's going to first pass through that thin protective layer here, the cornea, and then it's going to pass through the opening, which is our pupil, right? And the pupil will change size depending on the amount of light. So we talked with our cranial nerves. These are the nerves responsible for dilating and constricting the pupil. Keep in mind, dilating means making it bigger, and constricting is making it smaller. You want to dilate your pupil in dim light when you want to take in all of that information. You need more light. And in bright light, your pupil is going to constrict because there's too much light. So your pupil will change shape to regulate the amount of light coming into your eye. So light is going to pass through the cornea, through that opening, the pupil, and it's going to hit the lens. And the lens helps us focus for distance. In the same way you have a camera lens, and if you had one of those fancy cameras, you might turn the lens to help you focus on something. Or on your iPhone, you have portrait mode, which focuses the lens really close. And you've got the regular mode, which focuses the lens further away. So your lens in your eye is going to do the same thing. It's going to focus that light so that the light can hit the back of the eye. In a camera, the lens is going to focus the light so it can hit the film, or in digital cameras, the computer chip in the back of the camera. Your eye works the same way. The lens is going to focus that light so it hits the retina in the back of the eye. So once the light is focused by our lens, it's going to pass through this vitreous humor, this fluid in the back, and it's going to hit the retina. In the retina, remember, it moves in an inside-out pattern. So it's going to hit the photoreceptors in the very back of our retina. Those are our rods and our cones. It will then pass that information to the bipolar cells. Remember, rods are for black and white, shades of gray. We use our rods at night and on our periphery. And cones are more in the center, and they're for color. C for center, C for color. Cone, C. Okay. We have 3 types of cones. We got cones for blue light, green light, and red light. Not yellow. There's no yellow cone. Don't tell me there's a yellow cone. There's not. Okay, so the different photoreceptors, either rods or cones, depending on what kind of information it is, they're going to send that information to bipolar cells, which will then send that action potential to the ganglion cells, which become our optic nerve. That is where we had left off last time. We traced all of these parts, and then we had talked about some disorders. We talked about cataracts, and we talked about glaucoma. Okay, let's talk about what our eyes are meant for, what your eyes are meant for. So, eyes are made for distant vision. Your lens at rest, so if you're not squeezing your eye, if you're not squinting at all, your eyes at rest are meant to take in light from far away. The top picture here is showing you waves of light coming from a distant source. They're going to approach the retina, approach the lens rather, and the lens is going to focus it onto that fovea centralis, that focal point, okay? However, when light comes from a closer source, you have to move your lens, you have to use that lens to focus it into that back part near your retina. So we call that accommodation, which is when you focus on a close-up object. And if you do that for a while, you're going to notice that your eyes get kind of tired. And that's because those little muscles in your eye are having to hold and move your lens to focus on close-up vision. This is why they recommend, if you're looking at something on a screen or on your desk, that you take a break about every 20 minutes for 20 seconds and you look 20 feet into the horizon. It's the 20-20-20 rule. So every 20 minutes, take a 20-second break, stare off at least 20 feet into the distance. This will relax your lens, will relax the muscles holding your lens, and is better to maintain the health of your eyes. How the image is formed on your retina. So in actuality, when the light comes through the lens reverses the image and makes it upside down. So it forms like a mirror image. In the same way, if you were to take like a little mirror lens and play with it, the image you would see would be backwards. The lens does the same thing. It makes what you see in real life reversed and upside down and very small. And then your brain is what takes that information and flips it and expands it. So what is processed by your retina is not what you actually see. Other thing that your brain does, so your brain flips the image and expands it. Your brain also understands visual fields. So this is showing you a picture of a brain with some eyeballs here in the middle part. And the visual fields here are shown in color. So if you're looking straight ahead, you're getting information from both your left and your right eye. But if you look just to your periphery, then only one eye is actually being involved. And what this is trying to show you is that information about the sides of your world are processed by opposite sides of your brain. So information that you see on the left side of your world, your left visual field, which is shown here by the blue and the green overlap, that information is going to be sent from your eye. And if you follow those blue fibers, it's going to be crossed over at a spot called the optic chiasm. So the left visual field, the left side of your world, is processed by the right side of your brain. And the reverse is true for the other side. So the right side of your world is processed by the left side of your brain. Okay? And if we follow that information, that flow of information, it's going to go through your optic nerve. It's going to cross at your optic chiasm. So again, we're going to send the information from the left side of the world to the right side of our brain, and the information from the right side of the world to the left side of your brain. It's going to pass through the thalamus. Remember, that's that relay station that says, this is visual information. Okay, send it on back. And it's going to end up in our occipital lobe, the primary visual cortex here. So again, left side of our world processed by the right side of our brain, right side of the world processed by the left side of the brain. Optic nerve going to cross over at the optic chiasm, pass through the thalamus, and end in our visual cortex and our occipital lobe. Okay, finally, let's talk about some common eye disorders, nearsighted versus farsighted. So myopia is when you are nearsighted. Myopia is shown here, the eye. There is a shorter vertical axis compared to the horizontal axis, so our eyeballs kind of squish it. And that is when the distance is blurry. This is the most common. It's what I have that gives me these these very thick eyeglasses here. My eye has a shorter vertical axis than horizontal axis, so nearsightedness is what we call it. I can't see far away. Last comment is hyperopia. This is where you're farsighted, so things that are close up are blurry. This happens to people generally as they get older. They get hyperopia, so there is a squishing of the eye in the other direction where the vertical axis becomes longer than the horizontal axis. This is why old folks, when they're wearing glasses, they'll go like this, and they'll try and see the paper, or they'll have to get reading glasses. That's because close up is now blurry and far away is better. And finally, some people have an astigmatism. So this is called an unequal curvature. Usually what it means is your eye has like a little bump somewhere, so it's not perfectly round. And what this means for your vision is that sometimes points might look like lines. So you might be looking at a dot and it might appear as a line. All of this can be fixed with glasses or contact lenses. Myopia and hyperopia can also be fixed pretty easily with laser eye surgery. So they will shave off bits of your eye so that it becomes perfectly round again. Yeah, gross. I'm never going to do that, but people tell me it's a great option. Okay. So that is the end of the vision unit. And now briefly I'm going to start the next unit on our ears. So learning objectives for this part, we're identify the structure of our ears and their functions, and we'll talk about sound localization. We'll explain the function of some of the structures in our inner ear. We'll define what hearing loss and deafness are, and then finally we'll talk about equilibrium in the biology sense, which has to do with balance. So understand this, we have to talk about sound again. So like light, sound is also a wave. Sound is a vibration that's propagated as a wave through a transmission media, usually the air. And there are two pieces of information about sound that is encoded in that wave function. The first is the frequency. So frequency is whether something is high-pitched or low-pitched. High-pitched being really tiny and squeaky, low-pitched being really low. That is the frequency information. And for humans, we can hear frequencies from 20 to 20,000 hertz, hertz being the unit of frequency. And frequency in the wave function terminology is the wavelength. It's the distance from one wave to another. Other information about sound that's encoded in that wave function that our ears need to process is the volume, whether something is really loud. And that is the amplitude of the wave function, or how tall the wave is. Taller waves being louder, shorter waves being wider. Okay, so frequency, high-pitched, those are things that have a small wavelength, they're very close together. Low pitch has a long wavelength, they're farther apart. Then volume, quiet. Low amplitude, loud, high amplitude. All of that in mind. Let's talk about how our ears get those two pieces of information, frequency and amplitude. So the ear is unique as a special sense organ because it houses two of our special senses, both hearing and what we term equilibrium, which is just a fancy way of saying balance. And the ear is divided into three areas. The external or outer ear, this is the part of your ear that you can see and grab and pierce with fun earrings. The middle ear, which is also called our tympanic cavity, this is an air-filled chamber that has some very small, unique bones in it that we'll talk about. And then finally, the inner ear. The inner ear is full of fluid, and that's where the magic happens. That's where the receptors are that do the hearing and do the equilibrium. Okay, this is the picture we're going to come back to over and over and over again. So your outer or your external ear is this auricle or pinna part. This is the part of your ear that you see. It leads into your external acoustic meatus or your auditory canal, which is the thing that you're not supposed to put Q-tips in, but everyone does. And ending in your tympanic membrane, which is termed your eardrum. And your tympanic membrane starts your middle ear. So your middle ear is this little air-filled cavity in here with three tiny bones called ossicles. I'm going to use the Latin term for your ossicles, the malleus, the incus, and the stapes. The mis, malleus, incus, stapes. Little teeny ossicle bones in here. And then it's going to end in your oval window. And your oval window will start this fun spiral-shaped bone here, which is filled with fluid. And this is where you're in your inner ear here. This is where the receptors are for hearing and for balance. Okay, let's break it down into those 3 segments. So your external ear, this is just involved with hearing. It's got your auricle leading to your external acoustic meatus, which is lined with skin, and you have wax glands. You're not supposed to use Q-tips in your external acoustic meatus. And the Q-tip is for cleaning the outer auricle part. You should not be putting Q-tips inside, because what you can do is you can actually get an impaction of that cerumeum wax. You can get a wax buildup. And that can actually lead to worse hearing. So don't put Q-tips in your ear. Okay. The function of this external part is to funnel the sound in. So sound is coming from all over as waves, and your ear is actually shaped like a funnel. It's got these little ridges in it. It's going to help catch the sound waves and funnel them towards that auditory canal, towards your external acoustic meatus. So once the sound has been funneled in there, again, it's like a wave function, it's going to hit your tympanic membrane. Okay, so tympanic membrane. Oh, mute somebody. There we go. Okay, so our ears, our external ears, also help us with something called sound localization. Sound localization is you determining, or your brain determining, what direction the sound is coming from. If you ever notice, if you hear a loud sound, you can very quickly turn and look in the direction of that sound. That's because we get something called bi-aural cues, which are cues through both ears. And our brain is able to calculate the difference between when it hits your left ear versus your right ear, and do some fun math to determine, oh, it must have been in this direction. So it's able to determine where the sound comes from. And you can test this if you have someone close their eyes and you snap. You can pretty equally point at where that sound is coming from. Okay, so sound is funneled in through the auricle, goes down our auditory canal, and it's going to hit that tympanic membrane. And it is transferred to our middle ear, our tympanic cavity, which again is an air-filled cavity, only involved in the sense of hearing between the tympanic membrane and our oval window. And so the tympanic membrane will vibrate with that same wave function. So again, sound is a wave. As the wave comes down the canal, it's going to hit the tympanic membrane, and the membrane is going to vibrate, creating that same wave function in the air of our middle ear. The middle ear has an interesting feature to it, in that it has a connection tube. So the middle ear is considered this closed system, but it has a tube for equalizing the pressure. And this is called our eustachian tube. You also hear it referred to as your pharyngeal tympanic or your auditory tube. And it connects your middle ear to your throat. And so this is what you use to equalize the pressure. If you've ever been on an airplane before, you'll notice your ears pop, or if you go up in the mountains. And that's because there is a pressure difference between the air pressure on the outside world. So as you go up in an airplane or up a mountain, the pressure is going to fall, right? So you now have lower pressure on the outside in your external ear than you do in that tight air-filled cavity of your middle ear. And that difference in pressure can cause your eardrum to start bulging, start pushing towards the lower pressure side. And that actually can be quite painful. And so what your body does is it has this eustachian tube that will open up and allow for air to come into and out of that middle ear. It will open up that tight cavity and equalize the pressure. This is why when you go up a mountain or you go up in an airplane, they recommend that you yawn or swallow, because that's what opens up that eustachian tube, equalizes the pressure. In kids, they have a shorter eustachian tube and it's more horizontal. And so this is why kids cry a lot on airplanes. They have a harder time equalizing that pressure because of their eustachian tubes. So be respectful of kids on airplanes. It's not their fault that they're crying. Okay. In your middle ear, you have those 3 ossicles. These are teeny, teeny, tiny bones. Again, acronym is MIS. So malleus, incus, stapes. And what they do is they want to strengthen the wave function. So the wave function is going to come off the tympanic membrane. It's going to vibrate and create a wave. And if you've ever been in a swimming pool, let's talk about waves, the function of wave in air versus water. So if you've been in a swimming pool or a lake or an ocean and you jump underwater, you might notice that sound is kind of hard to hear, right? It's moving a little funny. You can't quite hear when you're underwater. And when you pop up, all of a sudden you can hear really well. And that's because when a sound wave moves through water, it slows down, it loses some of its strength. And so the function of our middle ear is to strengthen the wave function so that it can survive in the fluid of our inner ear. Your inner ear is fluid. We got to strengthen that wave so it can pass and move through that fluid. That's harder to do than moving through air. So again, we're going to take the vibration from our tympanic membrane, and that's going to move the hammer to the anvil, to the stirrup, otherwise known as the malleus, to the incus, to the stapes, and it's going to create a stronger wave function that will hit the oval window. So it strengthens the wave function in the same way that when you push a kid on a swing, you're going to strengthen their swinging wave, right? You're going to increase the wave by giving it a little extra oomph, okay? So the movement of those tiny bones is going to strengthen the wave function, which will then hit our oval window. Okay. Inner ear, otherwise known as our bony labyrinth, is where we have the organs for hearing and for balance. This has got a maze of little bony chambers in our temporal bone called the cochlea, and then the vestibule and the semicircular canal. So the cochlea looks like a little shell, it's like a little spiral. The vestibule is the area in the middle here, and then the semicircular canals look like little earrings, little hoop earrings. Okay, and all of this is suspended in a fluid we call perilymph. So there's fluid moving through all of these bones. If we focus on that spiral organ of Corti, that shell-looking thing, this is in our cochlear duct, and it has receptors that are hair cells on a basilar membrane. They're little teeny hairs on the membrane, and the fluid is going to move, which is going to move your tectoral membrane, and it's going to bend the hair cells. So as the perilymph in your inner ear moves, like a little wave, like a wave on a lake or a wave on an ocean, it's going to move the tectoral membrane, which is then going to push the hair cells in your cochlea. And when those hair cells are pushed, they will then fire an action potential. And that action potential will travel down our cochlear nerve and will transmit the impulses to our auditory cortex, which is located nearby in our temporal lobe. So this is what that looks like. We've got our basilar membrane here. It's got these little hair cells here shooting up these little hair receptors that are going to be bent by the movement of our tectoral membrane. And then we'll send that action potential down our cochlear nerve. So how that works again is the vibration from our sound wave hits the oval window. It's going to move the perilymph, which is going to move the tectoral membrane, which is going to bend the hair cells. And that action potential will travel and will eventually end up in our auditory cortex. This is showing you what that looks like again. So we've got that basilar membrane, those little hair cells, the tectoral membrane, and this is a zoom up of the hair cells. And so how the action potential starts is when they are straight up and down, the channels are closed. However, when they tilt, the sodium channel is a mechano-gated sodium channel, so that there's this little teeny string that will pull open the channel, and all of a sudden sodium rushes in. We got an action potential. An action potential is going to send a signal that you heard something. Okay. The last thing I want to talk about is how we hear frequency. So I told you the two parts of a sound wave are volume and frequency. Let's talk about frequency first. Frequency is encoded by which hairs bend. Frequency is encoded by which hairs bend. Different hairs bend to different frequencies. A high-pitched sound, a squeaky high-pitched sound, is going to disturb the short fibers near the oval window, where a low-pitched sound is going to move the long, floppier fibers further along, okay? So the hair fiber, this is what it looks like. This is our cochlea kind of untangled here, our basilar membrane. We have hair fibers of different heights. We've got short ones close to the oval window and long ones the furthest away. High-pitched noises are going to bend and move the short fibers, whereas low-pitched noises are going to bend and move the long fibers. So we encode frequency based on which fiber gets bent, okay? We encode volume based on the duration of that signal. So a really loud noise is going to keep the hairs bent longer. A really quiet noise. Duration that they bend is going to be what tells us about volume, and which hairs bend will tell us about frequency. Okay, that is where we are going to end today. So today, we finished talking about vision. Went through again how light is picked up by our eyes. We talked about how that information travels back on our optic nerve, how it crosses on our optic chiasm, so the left side of our world is processed by the right side of our brain, and the right side of our world is processed by the left side of our brain. We talked about some common reasons why people need glasses. Then we switched gears and we started talking about hearing. We talked about the structures of our external, our middle, and our inner ear. And we ended by talking about how we hear things, how sound travels and is processed by our ears. Okay. With that, we're going to stop for today. I will take any questions you guys might have. Otherwise, I will see you Wednesday when we finish hearing and balance and do smell and taste very briefly. You guys are good to go unless you have any questions.